Hey folks, welcome to this episode on properties and intermolecular forces. Now we have seen these different intermolecular forces before. We start off with London dispersion forces, which are created by the movement of electrons, dipole-dipole through the differences in electronegativity, a hydrogen bond, which is a very special form of dipole-dipole between a positively charged hydrogen and electronegative nitrogen, oxygen, or fluorine. And then we have an ion dipole, so something with a polar molecule interacting with a positive or negative ion. And as we can see, as we go up here, the strength of these intermolecular forces increases, which means that you'll need more energy as you go up in order if you want to break them. So a lot of the physical properties are due to the intermolecular forces in covalent compounds. As you can see here, again here you have a nice little hydrogen bond being created between these water molecules here, the negative side of the oxygen and the positive hydrogen over here. And a lot of these are some of the physical properties that that we're going to be dealing with in this episode. So states, the stronger the intermolecular force, the stronger the attraction, the closer the particles will be, and the kind of more solid the state was going to be. So when we talk about solid, they're going to be strong cohesive forces, and keeping everything really, really close. That means that you're going to have a very high density. This shape doesn't change, and the volume also doesn't change. So if you put this into this Erlenmeyer flask, it's not going to fill up the flask. It's going to remain as is, and you really, really can't compress it because the atoms are very, very close together already. When we look at liquids, there are weaker forces, and that allows the particles to actually slip and move over one another. Now, this allows you to take the shape of the container, but again, the volume doesn't really change. It's because it's still quite close to one another, so you can't compress it. So the volume doesn't really change, but the shape that it takes will take the shape of the container. And same with gas, it will take the shape of the container, but because the particles are very, very far apart due to these weak cohesive forces, you're going to have a low density. So obviously, remember, density is going to be mass over volume. So in this case, we have the same amount of volume, but we have less mass per unit volume. And because there's so much space between all these individual particles, it's going to be easily compressed. Our first property looking here is viscosity, and this is really the resistance of flow. So when we think about syrup or water, we say that syrup is more viscous, and this has to deal with the strength of the intermolecular forces that are between the actual particles that make up that substance. The stronger the intermolecular forces, the slower it's going to run, which we call more viscous. And here's a nice little visual. Here we have water, so you can only see that there are water molecules bonded to one another. And then we start adding different types of molecules that are kind of bonded in between the water as well. So you can see that the strengths of the bond are increasing as we go, which makes things move a little slower, aka be more viscous. Cohesion and adhesion, we've seen a lot of different properties. Cohesion is the attraction between like molecules. So if we have, for example, an H2O molecule, it's the attraction between those two molecules. Now, if it's in some kind of piece of glass, then the adhesion is the attraction between the water molecule and that piece of glass. So it's the attraction between different molecules, is adhesion and cohesion between same molecules. So when we look at this kind of tube, and I'm sure that you've seen this before when we're looking at test tubes or whatnot, when water is in the test tube, you get this kind of thing called a meniscus, which we'll talk about in a little bit. And this is really due to the adhesion between the water and the glass being greater than the cohesion between individual water molecules. So this water right here is pulling itself up the glass, bringing in inner water with it. Now, when we look at mercury, the cohesion between the mercury atoms is greater than the adhesion between mercury and glass. So it does form this kind of little sphere. Now, surface tension, you can see this wonderful diagram here of this individual swimming, and you can see the water kind of moving and taking the shape of the body, and kind of even looking at here, it kind of moves up where there's nothing there. And it results from the net inward attraction experienced by the molecules on the surface of the liquid. So in this case, here we have water, and this would be the water on the surface of this individual all the way there. Okay? Now, this water actually has an attraction for itself, and it actually pulls up the rest of the water to kind of join it to create this kind of nice little layer of water. And this is due to the cohesion between these in this case, water molecules. The cohesion comes from the intermolecular forces, the hydrogen bonds that water can create. So when we look at something like this, we put a little pin on top of the water, and we're able to float that. The attraction for this water molecule for itself, and then this one for itself, and that one exactly, etc., creates a nice little a tense surface here. And then you also have all this attraction in between here. Surface tension can lead to this phenomenon called beading and wetting. Beading is when you have water and it kind of beads up on a surface. So in this case, when we look at this apple, there's a lot of like beaded dots. Same thing here, there's a little bit more beading than wetting. Versus wetting, which is just a kind of nice thin layer of water. This has to again deal with cohesion and adhesion. When we look at beading, there's strong cohesive forces. That means that it's more attracted to itself than it is to the other substance. But wetting, there's strong adhesive forces, so that means that there's more attraction between the substance and the surface that it's on. Now, for example, this microsome slide, why is it one is wetting, one is beading? They put actually a different kind of layer on the slide. So one is more hydrophilic and one is more hydrophobic. The hydrophobic means it's scared of water, so it actually causes the water to bead up. The hydrophilic, and we'll just write that there is hydrophobic and hydrophilic. Okay? So the hydrophilic likes the water, so it's going to cause it to spread a little bit more thinly that way. This phenomenon that we saw in test tubes where the water kind of moves up and creates this meniscus is called capillary action. It's the ability of a liquid to flow up a thin tube against the influence of gravity. So in this case, both cohesion and adhesion play a role. There's cohesion between the individual water molecules on the surface, creating a surface tension here. But there is also adhesion on the edges of here. And the water effectively is pulling itself up the glass. As it pulls up the glass due to adhesion, the cohesion will actually bring the other water molecules up with it. Okay, so both forces are in play. Now let's move up a tube until the climbing force or the rising force meets the counter effects of gravity. So once those are equal, it's going to stop moving, and then we're going to just keep it in place. But we will form this meniscus because, again, these water molecules on the side or whatever this is will pull itself up against the glass, while these ones will be pulled up this way. And this is the meniscus. It's that curved surface that we see in thin tubes. Now, we usually see this kind of meniscus here, where we see, in terms of water, we see more of a concave. If you're looking that way, we're looking more of a concave meniscus. But here, when we're talking about mercury, we see of a convex meniscus. I'm going up. And this has to, again, deal with cohesion and adhesion. In the water, the adhesive forces, so the adhesive attractions, are greater than the cohesive. So that means that the water will try to climb up to the edge, okay, and pull the other inner water along with it. However, in mercury, the cohesive forces are greater. So it's going to try to create a little kind of bead in the sense, but it still is interacting with the glass, except in a less way. So the priority in this case is the cohesive forces between itself, and then its adhesive forces between the glass. Melting point, boiling point, volatility. Melting point is the temperature at which a solid turns into a liquid. Boiling is when a liquid turns into gas. And volatility is the ease of evaporation. And basically, all of these increase generally with stronger intermolecular forces. So the more hydrogen bonds you'd have the higher boiling point or melting point versus something that has London dispersion forces, which might have a lower melting point and boiling point. And solubility, it's the ease of a solute dissolving in a solvent. And this is a really interesting one because here we have water which has hydrogen bonds to itself. And here we're trying to dissolve some sodium chloride, NaCl. So what happens is that these water molecules have, again, hydrogen bonds to themselves. And in order for this to actually dissolve this sodium chloride, it has to first break the intermolecular forces between itself and establish new ones between whatever it's trying to dissolve. So in this case, here we have water that's now created an ion dipole. And this is an ion dipole because remember the water is polar and the Na is a cation, so ion dipole. Between these water molecules, you have hydrogen bonds. Now, remember how we were talking that ion dipole is stronger than hydrogen bonds. This results in something that's able to dissolve because the ion dipole bonds that are created are stronger than the hydrogen bonds. And this is a necessity for solubility. If you're able to break apart your solute bonds and solvent-solvent forces and creates a stronger solute solvent force, then this is favorable and this is going to result in solubility. But for example, when we look at something like if you were to put NaCl into some nonpolar substance, well, in between these nonpolar molecules, what do you have? You have London dispersion forces. You're not going to be able to create an ion dipole because you have no polarity in these nonpolar substances. So the best you'll be able to do is London dispersion forces, and that's really not different. So solubility might happen, it might be very, very small, but it won't be something as soluble as NaCl in water because you're breaking these weaker hydrogen bonds to allow the formation of stronger ion dipole forces. Now, one kind of rule that we like to go by is like dissolves with like. So polar substances will dissolve in polar substances, nonpolar in nonpolar substances. But if you try to dissolve polar into a nonpolar substance or nonpolar into a polar substance, that generally doesn't happen. Again, these are only guidelines. There are some exceptions, but that is the general kind of rule, and you do see that it works most of the time for our purposes. So that's it for this episode. Thanks very much for watching. We'll see you soon.